Bristol Community College, Mathematics with Dan Avedikian, Math 131, Elements of College Mathematics, Section 3.3, Problem 3. This is Section 3.3, Problem number 3. It says Ned the Nerd can make Captain Kirk action figures and Captain Picard action figures. Ned has 3,000 minutes of labor time each week to work on these action figures, and he has 3,900 ounces of special action figure making plastic that he can use each week. Each Captain Kirk action figure takes 10 minutes to make and uses 15 ounces of plastic. Each Captain Picard action figure takes 12 minutes to make and uses 13 ounces of plastic. If Ned makes $8 of profit on each Captain Kirk action figure and $10 of profit on each Captain Picard action figure, how many of each should Ned make per week in order to maximize his profit? So, like the other problems in this section, it's a 4-step process just to really even set up the problem, and then 4 more steps to solve the problem. So the 4 steps to set up the problem, step 1 is identify your variable, which is the 2 things being made. You want to figure out what 2 things are being made. One is X, one is Y. Now in this particular problem, there's 2 types of action figures, Captain Kirk and Captain Picard, of course the Star Trek captains. So whichever one is mentioned first, typically I'm going to just make it X. I just go in order. So Captain Kirk comes out first, so Captain Kirk is going to be X. So X equals, and I'll just put Kirk. You can write Captain Kirk, but we can abbreviate a little bit. And the other one, Y, will be Captain Picard. And again, you can just write Picard. So that's step 1, identify your variables. There you go. Step 2 is write out the object function. Look for information that's typically about profit, and it's usually near the very end of the problem. Again, not every single problem, but that's very typical. This one is a pretty typical problem. Near the end, it does say that Ned gets $8 of profit for Captain Kirk and $10 of profit for Captain Picard. So we're going to write maximize Z equals, so Captain Kirk is X, and every Captain Kirk is going to get Ned $8 of profit, so 8X plus every Captain Picard is Y, and every Captain Picard gets us $10 of profit. So 10Y. So there's our object function. Step 1, identify a variable. Step 2, write the object function. Step 3, set up the constraints. So step 3, we're going to write subject to, and what's going to limit how many action figures can be made is the number of minutes of labor, 3,000 minutes of labor, and the amount of special plastic, 3,900 ounces of plastic. So these are going to make up our 2 constraints. So I'll write the 3,000. I'm going to give myself a little bit of space, and I'll put labor. And the other one is the plastic, so that is 3,900, and that's plastic. So now as I read through it, it says each Captain Kirk action figure takes 10 minutes to make and uses 15 ounces of the plastic. So Captain Kirk is X. So for labor, since Captain Kirk takes 10 minutes to make, we're going to have 10X. And in terms of the material, the plastic, each Captain Kirk takes 15 ounces of plastic. And again, Captain Kirk is X, so 15X. So Captain Kirk is X, so you have 10X in the labor constraint because it takes 10 minutes to make a Captain Kirk, 15X in the plastic constraint because it takes 15 ounces of plastic to make a Captain Kirk. Again, Captain Kirk is X. Next, we can do Captain Picard. It says each Captain Picard action figure takes 12 minutes to make and uses 13 ounces of plastic. So, again, Captain Picard is Y. So 12 minutes to make, it's going to use 12Y in terms of the labor. And 13 ounces of plastic. So again, Captain Picard is Y, so 13Y for the plastic. So again, Captain Picard is Y, 12 minutes of labor to make every Captain Picard, and 13 ounces of plastic to make each Captain Picard. Again, in between the values we have in our constraints, we're going to have a plus, and each constraint is an inequality with a less than or equal to. If you have 3,000 minutes of labor, you can use all 3,000 or a little less, like say 2,980. You can't use 3,010 minutes of labor if you only have 3,000 available. It has to be 3,000 or a little less. Same thing with the plastic. You can use all 3,900 ounces or a little less. You can't go 3,920 because you only have 3,900. So that's the third step. Again, step 1, identify your variable. Step 2, write your object function. Step 3, set up your constraints. Step 4 is for each variable you use, it should be specifically mentioned that it's greater than or equal to 0. So the number of Captain Kirks that you make has to be at least 0. Can't make a negative number of Captain Kirks. Same thing for y, which is Picard. You can't make a negative number of Captain Picards. Of course, that's just sensible. So now we have the problem set up. Now we have to solve it. So now there's 4 more steps. Step 1 is graph your feasible region. Step 2 is label your corner points. Step 3, make the chart. Step 4, state your solution. So now for doing the feasible region, I essentially have 2 constraints. I don't count the greater than or equal to 0 as constraints. Those are easy. But my labor constraint and plastic constraint. So for the labor constraint, I'm going to make a line that's red on my graph. For the plastic, I'll do a different color. I'll probably go with green and start the graph. So for labor, let me make a little XY grid next to my labor constraint. Pretend this equals 3,000 minutes of labor. Find 2 points that satisfy that equation if you're pretending it's an equals. So now first, if I zero the x, what value of y would make 12y equals 3,000? So that's not something that's dividing out easy in my head, so I'll use my calculator. So 3,000 divided by 12 equals 250. And for a second point, let me zero the y. This one I can do in my head. 10x equals 3,000. So when you divide by 10, it's going to take one of the zeros off the 3,000. You'll have 300. So for the labor constraint, I have 2 points to graph it, to graph my feasible region. So now the plastic constraint, let me find 2 points for that. Again, I'm going to do it in a different color to make my work nice and clear when I graph it. Let me pretend my labor constraint is 15x plus 13y equals 3,900 instead of less than or equal to 3,900. And I'll make a little xy chart next to that. Find 2 values that make that equation true if I pretend it's an equation. So first, if I zero the x, I have the 15x just zeroes out. 13y equals 3,900. I know 3 times 13 is 39. So it's going to be 300. That one I can do. The other one looks kind of tough. If I zero out the y, the 13y will go away. I have 15x equals 3,900. I'd have to divide away the 15 to solve for x. That's not something that goes easy in my head. So I'm going to rely on my calculator for that one. So let me do 3,900 divide by 15. That'll solve for x. And it's 260. So now I'm ready to start my graph. Now, the numbers on my graph are going to be pretty big, 250, 300, 260. I definitely don't want to go one at a time. I want to pick a number scale where I can get up to 300 pretty reasonably. So 100 at a time would work pretty conveniently. Even 50 at a time, I'd only need 6 lines. 25 at a time would be okay. You could do 12 lines. You could go either way. As long as you label it clearly, I'm going to go by 50 for both the x and the y, which you don't have to run them on the same interval as long as they're labeled, but for this particular problem, it works well. So for the x, I had started it. I chose to do 50. So if I do 50, 100, 150, 200, 250, 300, I'll be able to accommodate all the x's that I'm going to have to put on my graph. Same thing for the y. If I do 50, 100, 150, 200, 250, and I'll squeeze in 300 at the very top, I'll be able to accommodate all the y values that I need for my graph. So now let me put the labor constraint on my graph. Again, I started that work in red, so I'll draw the line in red. So I'm going to put in one dot on my graph, one red dot, by going over 0 up 250 on my graph. So I'm going to put a red dot at over 0 up 250 on my graph. I'm going to put a second dot over 300 and up 0. Go over 300 and up 0. That gives me another red dot. I'm going to connect my two red dots with a straight red line. And now I have to determine whether I want to shade below that red line or above it. So the process is choose a test point that's not on the line. I like to use 0, 0 whenever I can. And see if the result you get when you put in the x and y values of your test point into the x and y of your constraint. See if you get a true or false statement. So if x is 0, y is 0, I have the statement 0 is less than 3,000. That's certainly true. 0 is less than 3,000, a lot less. So my test point was on the underneath side. My result is true, so that means the test point is in the shaded region. The underneath side is the shaded region. So that takes care of the constraint for labor. Now let's do the one for plastic. I'm going to do that in green. Again, the different colors make it stand out better. So to put the green line on into my graph, I'm going to put a green dot at over 0 up 300. That's the first point I had when I was working on the plastic constraint. So I'm going to put a green dot at over 0 up 300. And I'm going to put a second green dot at over 260 up 0. Now, my number scale that I chose to work with doesn't exactly have 260. It goes from 250 to 300. So by eye, estimate where the 260 should be and put a green dot, or whatever color you want to use, at over 260 up 0. So now I have two green dots on my graph. I'm going to connect the two green dots with a straight green line. And now I want to determine whether I shade above the green line or below the green line. So as I use the test point that I like, 0, 0 is not on the line, I can use it. See if the result I get from using 0 for x, 0 for y gives me a true or false result in my constraint that I'm graphing. So I get the result 0 is less than 3,900. Definitely true. 0 is smaller than 3,900. So my test point was on the underneath portion of the green line. The result is true, so it's the underneath portion of the green line that's shaded. And I won't even continue to shade above the red line. Now, the other two constraints, x is greater than or equal to 0, is going to keep my shaded region to the right of the y-axis. I can only have points in my feasible region where the x-coordinate of the point is positive. And the last constraint, y is greater than or equal to 0, is going to force me to stay above the x-axis with my shaded region. I can only have points in my feasible region that have a positive y-coordinate. And now, where all the shading overlaps, that's my feasible region. And it is a bounded feasible region. Now, the next part of the process that I've graphed the feasible region, next I have to label the corner points. And one corner point is over 0 up 250. So I will label that. 0 for the x-coordinate, 250 for the y. The next one coming around is 0, 0. Certainly not the maximum, but it is a corner point, so I will include it. The next corner point, it's not 250, 0. It's 260, 0 from when we graph the constraint for the plastic available in green. So that's 260, 0 over 260 up 0. And now there's a corner point where the red line for labor and the green line for plastic intersect with each other. And that's not that easy to read off the graph. Looks like it's over 150 up, maybe 125, but to really figure it out, what I need to do is solve these as equations simultaneously. Take my constraint for labor, take my constraint for plastic, write it as an equation, and solve simultaneously. So let me put that right here. So I am going to do, for labor, 10x plus 12y. I'm going to do equals 3,000. I want to write it as an equation. And then the one for plastic is going to be the equation 15x plus 13y equals 3,900. Now, my goal is to either cancel the x or cancel the y and solve for the other variable. And I could do either one. The x seems much easier. The y would be kind of tough. The x, I can go with 30x and negative 30x. That'll work nice. The y would work too, but much more work on my part. So the top equation, to turn this 10x that I have now into a 30x, every part of my top equation will be multiplied times 3. So I'll have 10x times 3 is 30x. 12y times 3 is 36y. And then 3,000 times 3 is 9,000. And then the equation underneath, I now have a 15x. I'd like it to be a negative 30x. Not just 30x, but negative 30x. So every part of this equation will get multiplied times 2. Negative 2, not just 2, negative 2. So 15x times negative 2 is negative 30x. And then 13y times 2 is negative 26y. And then 3,900 times negative 2 will be equals negative 7,800. Now I can combine the two equations. My x variable will cancel, which is good. So 30x and negative 30x cancels the x's. Positive 36y, negative 26y will give me a positive 10y. And now positive 9,000, negative 7,800 will be positive 1,200. Now I have 10y equals 1,200. I can divide out the 10, which is basically going to cancel y off the 1,200, and it'll give me y equals 120. So the point of intersection that I'm working on between the red line and the green line has a y coordinate of 120. Now looking at my graph, that seems pretty good. Let's see how the x comes out. I had said about 150. What I want to do is take that y is 120, go back into either equation, and find the value of the other variable, in this case the x. So let me pick the top one, just because the numbers are a little bit smaller, they seem a little bit easier to work with. Again, I should be able to use either one, get the same answer. I picked the top just because it seems like it'll be less effort on my part. So this is going to become 10x plus 12 times y becomes 12 times 120, now that we know y is 120, and that's going to equal 3,000. Now 10x equals 12 times 120. Well, 12 times 12 is 144, but I need to have a 0 on the end because it's not 12 times 12, it's 12 times 120. And that equals 3,000. Now I want to bring the 1440 I got over with the 3,000. I'm going to subtract it away. So I have 10x equals, when I subtract that, it's going to be 1560. And now if I divide out the 10, 10x equals 1,560. Again, the 0 from the 10 is going to cancel the 0 on the end here. So x is 156 actually. So the graph, it looked like 150. In reality, it's 156. So that you wouldn't have been able to read off of a hand-drawn graph. You really have to solve simultaneously like we did there. Now that I have all the corner points labeled, what I need to do is set up that chart where I plug them all in. It looks like I have a nice spot for my chart right here. Let me put it there. Again, I'll go with a different color. I've got a lot of red here. I don't want it to blend in too much. So let me do it in this purple color. So I have one column where I list my corner points. The middle column I leave a little bit wide. I put in the object function, which for this problem is z equals 8x plus 10y. And my last column will be for output. Let's see, I have 4 corner points. I'll make sure that I have 4 rows in my chart. List out the corner points. So I have one at 0, 250. So 0 for x, 250 for y. I have one at 156, 120. 156 for x and 120 for y. I have another corner point at 260 for x and 0 for y. And the last one's 0, 0. Again, I know for sure that's not the maximum, but I'll include it. So now start plugging the corner points that we listed in the left column into the object function. Z equals 8x plus 10y. So now 8x for the first corner point becomes 8 times 0. 10 times y becomes 10 times 250. 8 times 0 is 0. 10 times 250 is 2,500. And now if we add 0 plus 2,500, the output is 2,500. Now that means Ned can make a profit of $2,500 by making 0 Captain Kirks and 250 Captain Picards. Basically use up all your resources making as many Captain Picards as you can, because they sell for a little more. The next corner point that we're going to test the output for, 156 for x and 120 for y. So 8x becomes 8 times 156, and 10y is 10 times 120. Now 8 times 156, if I really had to, I could figure it out without the calculator, but it's just so much easier this way. 8 times 156 equals, the answer I get is 1,248. 120 times 10, the times 10 is going to put another 0 on it, so it becomes 1,200. And now if I add 1,248 plus 1,200, it's going to be 2,448. Wow, almost the same. So that's telling you that Ned the Nerd can make a profit of $2,448 by making 156 Captain Kirk action figures and 120 Captain Picard action figures. The next corner point down, the x value is 260, the y is 0. So 8 times x is 8 times 260, and 10 times y is 10 times 0. So again, 8 times 260, I'll just do with my calculator, 8 times 260. Is 2,080. The 10 times 0 I certainly don't need my calculator for. So I have 2,080 plus 0 is 2,080. Again, which means Ned can make a profit of $2,080 by making all Captain Kirk action figures. 260 Captain Kirks and no Captain Picards. And the last one, 0, 0, is going to give me a profit of 0. 8x is 8 times 0. 10y is 10 times 0. That'll make 0 plus 0, profit of 0, which is not what we want. So we want to maximize the profit. The different possible levels of profit we can make are $2,500 profit, $2,448 profit, $2,080 profit, or $0 of profit. Well, the best is we want $2,500 of profit. So for the state your solution, let me write over here, maximum profit of $2,500, put a dollar symbol in front, by making so that point was 0 to 50, so 0 Captain Kirk and 250 Captain Picards. And that's the answer.